Folks, for reasons having everything to do with how much of a turd sandwich the last couple of months have been, but very little to do with the current global health crisis, it's been a while since we've looked at a graphics card, but that ends today.
On the bench here, we've got this beautiful Sapphire Radeon R9 390 Nitro, that's a mouthful, that came to us in the same lot as the 980 Ti we looked at last time. Now, I was excited to see this card in that lot. In fact, almost as excited as I was about the 980 Ti, because I've never actually seen one of these 300 series cards in person. These didn't sell very well because they're not much of an upgrade over the 200 series, and I suspect everybody who wanted one already had a 200 series and skipped these. But we've got one on the bench today, and I'm stoked to look at it. Now, I admit I've already cheated and taken some measurements on it, so I have some idea what's going on before I turn the camera on. But before we get started, let's go ahead and take our 12-volt rail resistance measurements so that we know what those should be in case you're working on a similar card and you need to sanity check what you've got. So let me grab my meter here, and we'll get after that. All right, we've got our meters set up. We're in resistance mode. And the pin you want to probe, on this card at least, is this one right here. See, the latch is right here. You want the row of pins away from the latch and the one all the way to the right when looking into the connector, and the latch is on the top. So we'll go in here, and what we're going to see is, come on, there we go. That will count down into the single-digit millions. And I haven't been able to get this one to stabilize, but if you're seeing single-digit millions like this, this is probably okay. And it does that every time. I wonder if there's something going on with some sort of switching logic. Anyway, this is what you're expecting to see. Single-digit millions. So let's try the other one here. And I think we should be expecting about 10K? 10, 11K. Something like that. This looks healthy. This is what we normally see on the 12-volt rail when we do this test on most graphics cards. Particularly AMD cards. They tend to be designed this way. So that looks healthy. This other one is odd, but I suspect okay. And we've got one more rail on the PCIe finger, and we'll do that one as well. And I strongly suspect that we can probe that on this little fuse guy right here. And we got single-digit thousands, so 5.4. That looks okay. All right, so with that measurement out of the way, let's plug the card into the test bench and fire it up and see what happens. We don't have any reason to believe currently that the card's going to catch fire or anything, and I know because I've already tried this that it's not. So we'll go ahead and plug it in and see what happens. With our card hooked up to the test bench, we're just about ready to start it up. But first, let's just take a look for a moment at the back of this, because I want to point out that we can take some measurements without disassembling the card at all by reaching through these little holes in the back plate to some of the components on the PCB. So we can easily measure the core voltage through here. We can measure what I think is the 5-volt rail through this guy. These things are usually the 5-volt rail, and this one, I know because I've cheated and I looked at this. This one is the 3.3 volts. So if we go ahead and start this up, we get nothing on the screen. Note, we've got a display hooked up here, but we're getting nothing on the monitor. So the card is not starting up and running in any way. So let's go ahead and check what we can with the card assembled. So we'll test this output. And what we're looking for there is 5 volts, so that's good. And we'll test this guy. 3.3, so that's good. And we can also reach the back of our core here. So let's test that. And what we're going to get is 200 milliohms. So this may be leakage through something to the core, or it may be that the VRM is partially running and not running correctly. And without taking this apart and doing a little more digging, we don't know for sure. So we're going to go ahead now and shut our test bench down. And we need to get on with disassembling this. so we can see if there's any physical damage or anything else that gives us a clue as to why that's happening. Alright folks, what was just a moment for you was actually several days for me, and I've had quite a while to look at the card, which you can see is now disassembled, and we've got the heatsink off. And what we're looking for here is any evidence of obvious mechanical damage, burn marks, craters, scorched components, that sort of thing. And you'd be forgiven for not being able to tell in this YouTube video, but I don't see anything on this side or the back. If we flip it over, we can look at the back here. I don't see anything on either side that is obvious evidence of a failure of any particular component. I do think I know what's wrong, but it's not really based on any visual inspection. Nevertheless, our next step in the diagnostic process is to take some resistance measurements to make sure that all of our voltage rails have the proper resistance to ground. So we'll go ahead and start up our multimeter here. The first thing we're going to test is resistance to ground on our 12-volt rails. Remember, we had sort of an oddball reading on this one. We had what we believe is normal on this one. So let's start with that one. And it should be this pin. So we've got the same oddball reading there. And if we test here, still got oddball readings. One thing to note about this card is that the designers were good enough to include fuses for our 12-volt input rails. We've got 2 here and 2 here, and we've got another one over here for our 12 volts in from the PCIe connector. So one test we can do that will quickly tell us if we have a short or something somewhere, which part of the card it's in is, are any of these fuses blown? So we'll start with this guy over here. And what we're going to look for is basically 0 ohms on these. So we got 0 on that one. So that one is good. Let's try one of these guys. And there we've got all sorts of out of whackness. So one thing that we know very quickly, just from testing that, is that these 2 fuses, these are connected, right? Yeah. That these 2 fuses are blown. What about these ones? So we'll probe there. And that one is good. So very quickly we've determined that we have a blown fuse on this set of fuses, which I suspect is connected to that power rail. So if we test here, what we should get is 0. Yeah, okay. So we've got these 2 fuses that are connected to this power connector, and that basically tells us that somewhere we had a short that caused these fuses to blow, and that's why we get this wacky reading on this power connector. So what we need to do is figure out what these are connected to on the card. And if I had to guess, I would say it's probably something like the components in this area. So we'd have like this one reaches down and around over here. Let's check that out. So if we do this, and I know from looking at the data sheet that this little pin right here is the 12-volt input pad for our DRMOS. So if we test here, we've got continuity there. Got continuity there. There. But not here. Okay. So what about this one? Yeah, okay. This phase, and probably the rest of these, let's check. Yeah. 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 And maybe here. Yeah. Okay. So these three phases plus our memory power are hooked up to these two fuses, which are blown. So somewhere in this part of the card, we have probably a short to ground. So one way we can test that is we check our resistance from there. Remember, this is the 12-volt rail inside the fuse. So if we go from here to ground, what do we have? 0. So yeah, we have a short somewhere in this area. Now, before we go on, we should probably take some other resistance measurements just to make sure that we don't have anything destroyed on the rest of the card that would make trying to repair this moot. So let's try our V-core rail. Let's see. Okay, so we know from past experience with these GCN cards that 1.5 to 4 ohms is good. So 2.6 is right where we think it should be. And then if we go up here, what do we got there? Okay, that's ground. What about this side? Okay, that's still V-core. What about these ones? So what we're looking at now is this area. Hang on. All right, sorry about that, folks. As I was saying, we need to check resistance on our memory rail. And the last capacitor we tested was part of the V-core. So let's see if we can't find one for the memory. So that's probably this right here. So maybe there? Yeah. Okay. So 100 something is perfectly okay for the memory on one of these cards. So now we need to check our memory controller, which is this over here, and maybe one of these. Okay, that's ground. 69. That's actually a little high, but it's not terrible. That's probably all right. So what do we got here? This is our PCIe 12-volt input. That's looking okay. We've got one VRM here. If I had to guess, this might be... Okay, that's probably our display drive or whatever it is that is. That one looks all right, if a little low. That looks okay. All right, so without doing some more testing that I don't think we need to do right now, these two rails we don't know the function of, but they have a reasonably sane resistance, something in the range of a few hundred to a few thousand. So we're going to say those are okay, and we'll test just a couple more. So here's our 5 volts. That looks all right. What else do we got? I think we can conclude that all of our low voltage DC rails are probably okay. And the problem is mainly that we have a short to ground on our near 12 volt power connector. So we need to figure out where that is. And if I were going to guess where that is, I would say it would be one of these DRMOS power stages. These guys right here. These are relatively weak for a card that draws this much power, presumably for cost reasons. Sapphire presumably figured out that, hey, we could probably use the cheaper version of this instead of the more expensive version. But one thing that we may notice is that the pads that these are installed on are actually wired up and have the right pads for the bigger version. This one is the IR3553, and there's a 3550 that's 50% more powerful than these. And if we can get the card working, it might be an interesting experiment to see if we can swap these out for the 3550s and make the card a little more robust and or better at liquid nitrogen overclocking if that's your bag. But first we obviously have to get the card working. Now, under normal circumstances, I would have said it's probably one of these power stages that is the problem, and we can just start removing them until we clear the short. However, I was looking at the card the other day, and you won't be able to see it on the video, but one of these little caps right here, this one, is different from the others. It's kind of bulgy, and if you run your fingernail across it, right there, it's like there's a crack or something in it. And that is a classic sign of a capacitor that may be in short. Without removing it, we won't know if that's where the short lies. So I think our first actual diagnostic action that we're going to take, now that we've taken some measurements and we know that it's somewhere in this area, is we're going to remove that capacitor and see if that clears the short. So I'm going to fire up my soldering iron, and we'll go ahead and remove that and see if that fixes our problem. Now, you may wonder why I'm not using the hot air for this, and the reason is I'd like to be as uninvasive as possible so that, especially if this is the problem, I don't risk damaging anything else by heating up the whole board. Also, there's a ton of copper in this area that we'd basically have to heat all of it up in order to get that one little capacitor off. And I think some skillful use of my soldering iron will allow me to just heat this from the side and heat up both sides at the same time, and I can just pull it right off. So let's get some flux on there. Like that. 1 Lewis Rossman's worth of flux. Alright, heck with it. We'll use the hot air station. Alright, there we go. We got our cap off the board, and now we'll let it cool down and take another resistance measurement on our 12-volt rail and see if that cleared our short. If not, then I think the next step is probably the power stages, which are the next most likely culprit. But this cap sketched me out, so that's what we tried first. So, I will be back in just a minute once this is cooled down. Alright, just a minute later, and we're ready to test our resistance across our 12-volt rail to see if we were able to clear the short. So, the simplest place to test is the pads that we just removed the cap from. And what we're looking for is thousands, just like that. How about that? So that's a good sign. That means we've cleared our short. And if we test some of the other phases, you'll see we get a similar resistance measurement. Thousands. And if we test from our coil to ground, we should also get something similar to that. See that? Okay. So further, if we look at our removed capacitor here, let's put our meter in beep mode. Check this out. Oh, you're not doing it for me now? I see how it is. There we go. See that? We've got a short through this cap. With the short cleared, we need to get another cap to replace this. And unfortunately, I don't have one on hand, so I'm going to have to order that from the internet. But you may remember that on this side of the card, we had these fuses, which are also blown. So we're going to need to replace those as well, and I certainly don't have those, so I'll have to go get those from the internet. And that means we're going to have to reconvene at a later time. But things are looking up. One way we could test to see if we really fixed the card is we could just solder a wire over this and plug it into the test bench and see if it runs. But I think that would probably be an unwise thing to do. There's no guarantee that it would damage anything, but we don't need to do that. We're not in any hurry, so we're going to do this the correct way and get the right parts. So, I'm going to figure out what the capacitance of that capacitor is by removing it, and also get some of these fuses on the way. And we will reconvene once I've got the parts in hand and we're ready to install and test them. So until then, I hope you found this interesting, and if you're working on your own 390, I hope this helped you out. And as always, I'll see you in the next one.